All right, is it time? Yeah, it's time. Okay, let's see. Where were we at last time? Let's say the 14th. This pen seems weird. No, okay, it's fine. Last time we were talking about projections. So really kind of finding a vector that's in the direction of it, or how much of a vector is in the direction of another vector, or I should say the vector that is how much of another vector pointing in the direction of another vector. Here is what we did last time, just to kind of refresh our memory. So we had two vectors, um, A and B, and some angle between them. And we essentially were dropping a perpendicular from B onto A. And, oop, wrong pen, sorry. And this vector here, that is the projection of B onto A. And we calculated it last time. Oh, that looks very blurry. That's better. So last time we calculated, we found two things. We found, first of all, that the length of the projection, which we call the component of B onto A, turn like this, component of B onto A, and that was equal to A dotted with B divided by the magnitude of A. And then we said the projection vector is just the length of the projection vector multiplied by the direction of the projection vector, which is just A dot B divided by the magnitude of A multiplied by the direction, which is in the direction of A. So it's A divided by the magnitude of A. And again, the idea here really is that you're essentially saying, I'm going to find this little unit vector right here. That's your A divided by the magnitude of A. And then you're multiplying that vector that's pointing in the right direction by how long the actual vector you want is. Fairly not terrible, kind of. I never remember it like this. I would always prefer to write it as A dot B divided by the magnitude of A squared times the vector A, or as I mentioned, I think last time, A dot B divided by A dot A, all times the vector A. So that's what we did last time. We talked about it a little bit. I feel like there's one other thing I meant to say here. Sure. And yeah, let me just point this out one more time. One more time. This part here, that's the length of your vector. And this right here is the direction. Oh yeah, I know what it is. There is one more vector to talk about here. Color, sure, purple, fine. There's also this vector here, which we call, well, I'll label first as ORTH of B onto A. What do we call this? The orthogonal projection, projection is wrong. The orthogonal of vector B onto A. So orth of B onto A is the orthogonal, meaning perpendicular, vector that you get after you project B onto A, of B onto A. Whatever we call it, it's not nearly as terrible to calculate. In that if you've already calculated the projection, it's very straightforward to say, well, the projection of B onto A plus the orthogonal of B onto A. So you start here, you do the projection, you do the orthogonal, that just adds up to the vector B. So that if you're trying to find the orthogonal of B onto A, you're just going to do B minus the projection. And I would say very generically here, these kinds of things are probably easiest to find by drawing a picture. If you can draw the picture, be like, oh yeah, projection plus the orthogonal is B, it's very kind of straightforward to see that the orthogonal part is just B minus the projection. Okay, it's enough of like writing just letters and things. Let's actually do an example of numbers, right? It's just a little bit tedious. Be like, okay, here's all these things. So let's look at an example. So example, let's say that A is the vector 4, 3, and B is the vector 1, 4. And although we don't need to draw a picture here, I'm going to draw a picture just so we can see what's happening. So let's draw the picture. Try to draw it as nicely as I can. So let's see, we're going over 4, up 4. And the vector B is 1, 4, so we're going over 1 and up 4. So here's your vector B. And over 4 up 3. There's our vector A. And we're going to project B onto A, meaning from B, we're going to drop a perpendicular onto A. So this length right here is what we're going to find first. That's the component of B onto A. So the component of B onto A is going to equal A dot B divided by the magnitude of A. So that's going to be, let's see, A dot B is going to be 4 times 1 plus 3 times 4 divided by the magnitude of A. A was picked on purpose to have a nice magnitude. The square root of 4 squared plus 3 squared, which ends up being 4 plus 12 is 16, divided by the square root of 16 plus 9 is 25. So 16 over 5, or a little bit more than 3. Seems plausible. Seems like I might have not drawn it perfectly. Okay, that's fine. So that length is a little bit more than 3. Right? Yeah, more than 3. So then let's find the projection. Now, here's what I'd say about the projection. Since we already know the component, you could just multiply it by the direction vector. We could say it's going to be exactly 16 over 5. There's your length, multiplied by the vector A divided by its own magnitude, which would be, in this case, 16 over 5 times the vector A, which is the vector 4, 3, divided by the magnitude of A, which we just found to be 5. So this looks like we're getting 16 over 25 times the vector 4, 3. I don't really love multiplying it through here, but I will. 16 times 4 is 64, so you're getting 64 over 25 for the first component, comma 16 times 3 is 48 over 25 for the second component. So 64 over 25 is kind of like 2.5-ish, and 48 over 25 is pretty close to 2. So it kind of looks like we've gone over 2.5 and up 2. Okay, that seems reasonable. So there is my, in red, my projection. Wow, that did not get drawn as well as I would have liked to have drawn it. Sorry about that. So there's my projection of B onto A. Now, here's what I'll say about this. If I was actually just asked to calculate a projection, I probably wouldn't go through the process of first finding the component of B onto A and then finding the projection of B onto A. I'd probably just say, hey, I know the projection formula is going to be the thing I'm projecting onto is the one that shows up a lot. The thing I'm projecting shows up only once. So I know it's going to be A dot B divided by A dot A, all that times the vector A. And doing it that way, we should get the same result, but let's just see what it looks like. So A dot B is going to be 4 times 1 plus 3 times 4. A dot A is 4 times 4 plus 3 times 3. And then the vector A is the vector 4, 3. If we look at this, we get exactly the same thing we had before. 4 plus 12 is 16. 16 plus 9 is 25. We get 16 over 25 times the same vector. So it is the same result, but kind of a different way of thinking about how you calculate it. Either way is totally fine. Lastly, for this problem, let's find the orthogonal of B onto A, which always feels like a weird phrase, in my opinion. It seems like a weird thing to say, but okay. So this part should be the really easy part. The orthogonal of B onto A is just going to be the vector that you're projecting minus the projection. So in this case, our vector B was the vector 1, 4. Our vector that's the projection is 64 over 25, comma 48 over 25. I probably want a common denominator here. So let's say we've got 1, which is 25 over 25, comma 4, which is 100 over 25, minus 64 over 25 and 48 over 25. So we get a vector that's going to be 25 minus 64, which is negative, what, 49, I think? No, 39? Yeah, 39. Negative 39 over 25, comma 100 minus 48 is 52. And that should track with what we've drawn. This vector here, yeah, it goes left and up. So the x component should be negative, the y component should be positive. And that seems like reasonable values, a little bit like 1 and a bit and a little more than 2. Yeah, left 1 and a bit, up 2. Sure, that seems good. They're not very exciting problems, to be perfectly honest. Like they're just kind of like, okay, here's a thing you can calculate. How fun. Why do we care? Good question. Why do we care? We might care because of a problem like this, although I feel like it's debatable. So here is an example of how you might use this. Sure. So let's look at this problem. So this problem is actually just going to use the same stuff we've already done. So even though it's going to feel like a different question, it's really just an application of exactly the problem we just did. So here's the question. How far is the point 1, comma 4 from the line y equal to 3/4 x? Well, let's draw a picture. So the line y equal to 3/4 x is a straight line with the slope of 3 over 4. So we're going, starting at the origin, we have a rise of 3 and a run of 4. So we're going over 4 and up 3. So our line looks like this. I don't know, I wrote plus 0. Sure, that feels silly though. And then the point is the point 1, comma 4. So we're trying to find exactly how far it is if we drop a perpendicular from the point 1, comma 4 onto this line that we just drew. But that's literally the picture of the orthogonal vector that we just drew in the previous problem, right? If you look back, if you can look back, right? Same deal. This vector 1, 4, this vector b does terminate at the point 1, 4, and this vector 4, 3 is exactly on the line that is y equals 3/4 x. So we're really just finding the length of that projection. So this distance is the length, sorry, not the length of the projection, the length of the orthogonal of beyond A, apologies, is the length of the orthogonal vector we just found. So it's going to be, let's see, and I forget what that was. Let me look back. It was, oh yeah, the vector we just found. It was negative 39 over 25, comma 52 over 25. Let's, oh yeah, then I have an extra, I think I have a good question after this. So, fine question. What do I want to point out here? So then the length of that's kind of terrible. It's going to be equal to the square root of negative 39 over 25 squared plus 52 over 25 squared. And I can't think of any good reason to actually do that math. If you use a calculator, you get approximately 2.6. So here's a question that I think comes up enough that it's worth mentioning. Not this question, the next thing I'm about to say. So what if I asked you to, sure, what if I said find a unit vector in the same direction as the orthogonal vector we just talked about, orthogonal of B onto A. One way of doing that would just be to taking this gross looking vector and dividing it by this magnitude. But there is a less cumbersome way of doing this. So another option is to say, well, I can take any vector that points in this direction and divide that vector by its magnitude. So instead of the gross thing I'm about to write, so instead of answering this question with the vector negative 39 over 25 comma 52 over 25 divided by its own magnitude, which is that gross thing there, and really you don't want to write this down because it's just terrible. You could say, I'm going to multiply this vector by 25. And then say, I'm going to use the vector negative 39 comma 52 and divide that vector by its magnitude. It's still not lovely, but at least you don't have fractions and fractions. And these are the same. Literally, actually exactly the same. There is no difference between these. You've taken something of, so both these vectors point in, I'll say, this direction. It's just that this one, I took the actual vector and divided it by its own length to get whatever the unit vector is here. This one, I first took this original vector, made it 25 times as long, and then divided by its length, which was 25 times as long, to get back to the same unit vector. And this is in my opinion, a tactic that everyone should be taught because it's a very, very much easier way of normalizing or making a vector a length of 1. So if you have something gross and you have to make it a unit vector, it's totally fine to multiply it by any non-zero number you want and then divide by the magnitude of that new vector. I think it's kind of great. But that might be because I thought of it, so maybe it's not that great. Anyway, one more question about this, and then we'll move on to talk about matrices. Have you guys started talking about matrices yet? Cool. All right. So one more thing, and then matrices for the rest of the quarter. So there is a question in the textbook. I think it's 8.3, number 35. That's a little bit weird. So here's what we've got. If the vector A is equal to 3, 0, 1, we want to find a vector B such that the component of B onto A is equal to 2. And so here's the idea graphically. Again, not that you need to draw a picture. I just like to draw a picture so I can understand what I'm trying to think about. So here's my vector A. I'm just going to draw it kind of very generically. And what I want is to find some vector B like this, so that when I drop the perpendicular from B onto A, the length of the projection is exactly equal to 2. That's what I'm trying to find. Okay, so I know how to calculate these things, but first of all, let's say, since we don't know what B is, let's just say that B is going to be the vector with components B1, B2, and B3. And we know how to calculate the component of B onto A. I'll remind you, because I'll tell you, this might be the first time ever I've actually been able to remember this formula. Like usually I just don't know it. Like, why would you memorize this formula? I wouldn't personally, but if you do it enough, you end up memorizing it. So the component of B onto A is A dotted with B divided by the magnitude of A. Okay, and we want that to equal 2. So let's write it out. So A dot B is going to be 3 times B1 plus 0 times B2, I don't even want to write that down, plus 1 times B3. Divided by the magnitude of A, which is the square root of 3 squared plus 0 squared plus 1 squared. And that should equal 2. Well, it seems like we could solve this pretty easily, I think. So we're going to multiply both sides by this. So we're going to say that, yeah, we're going to say that 3B1, and I feel like I made a mistake here. Oh, I did. Sorry, I made a mistake writing down the problem. The vector A isn't 3, 0, 1, it's 3, 0, negative 1. Sorry about that. So this should actually be 3 times B1 plus negative 1 times B3. And it won't change the magnitude at all because negative 1 squared is still the same as 1 squared. So let's see. We're going to have 3 times B1 minus 1 times B3 equal to 2 times the square root of 10. That seems kind of annoying, but okay. But there's a lot of choices here, right? Literally like an infinite number of choices. Probably an easy choice would be to say like, I'm going to let B1 equal the square root of 10 and B3 equal the square root of 10. Because then 3 times B1 minus B3 is going to be 3 root 10 minus 1 root 10, which is 2 root 10. Or you could pick, I don't know, B1 equal to 0 and B3 equal to negative 2 root 10. That would also work just as well. Now, you might be asking yourself the question, what about B2? Well, since the A vector has a middle component of 0, B2 can actually be anything. So we could say one answer would be the vector B equal to root 10, comma, pick your favorite number, comma, root 10. But literally, you can put anything in there. And then using the other answer you've got here, you could say that another choice for B could be 0, comma, negative 17, comma, negative 2 root 10. And when you check, when you do the math, both of these, when you take the component of A with B, well, I should really say both of these, when you dot them with A, are going to give you 2 root 10. And then 2 root 10 divided by root 10 is going to give you 2. So there's a lot of answers there. They're all valid. Yeah. Kind of a weird question, but sometimes we ask questions like that. I think that's enough of that. So let's look at matrices. Matrix algebra. And let's start off with a couple of matrices. So let's say we have the following matrices. So the matrix A is the matrix 2, 1, negative 3, 5. It's pretty standard to read a matrix from left to right and then from top to bottom. So I'm reading the first row is 2, 1, and then the second row is negative 3, 5. And I should point out, because it is good to talk about the nomenclature here, that's row 1, that's row 2, this is column 1, this is column 2. This is a 2 by 2 matrix, 2 rows by 2 columns. Let's say that B is also a 2 by 2 matrix. B is going to be the matrix 4, 0, 1, 3. And sometimes if you want to talk about the size of a matrix, you write down in the lower right-hand corner that it's a 2 by 2. Although you usually don't write that if you've actually drawn the matrix, because you can see it's a 2 by 2. And then thirdly, we're going to have the matrix C equal to, the first row is 6, 1, 2. The second row is negative 1, 0, 1. And C is a 2 by 3 matrix, 2 rows by 3 columns. So some nice things about matrices. You add them as you would expect, meaning that you're just going to add component by component. So for example, if I want to say find A plus B, I would just have the matrix A, 2, 1, negative 3, 5, plus the matrix B, 4, 0, 1, 3. And then I should say the component in the first row and first column is going to be 2 plus 4. And then first row, second column, 1 plus 0. Second row, first column, negative 3 plus 1. Second row, second column, 5 plus 3. I would probably encourage you to skip this intermediate step here and actually just do the addition and get 6, 1, negative 2, 8. Or if you wanted to say find 2b minus a, well, when you multiply a matrix by a constant, just like when you multiply a vector by a constant, you just multiply all the components by that constant, or that scalar is another word we use for that. So here it's going to be 2 times the matrix B, 4, 0, 1, 3, minus the matrix A, which is 2, 1, negative 3, 5. So you could probably do this in your head, but we'll write another step here. So 2 times 4 is 8. So we're going to have 8 minus 2, and then 2 times 0 is 0 minus 1. 2 times 1 is 2 minus 3, and 2 times 3 is 6 minus 5. Simplifying that, we get the matrix 6, negative 1, 2 plus 3 is 5, and then 1. On the other hand, if I said something like, what's A plus C, we are out of luck, because A is a 2 by 2 matrix and C is a 2 by 3 matrix. And matrices of different sizes cannot be added or subtracted together. So this operation here is not defined. We cannot add or subtract matrices of different sizes. And so for matrices to be the same size, they have to have exactly the same number of rows and the same number of columns. Okay, so matrix addition, subtraction, pretty straightforward. So is multiplying matrix by a scalar. Matrix of multiplication, on the other hand, is a little bit more picky, complicated, specific. So let's look at, say, something like the matrix A times B. So A times B is going to be the matrix 2, 1, -3, 5, multiplied by the matrix 4, 0, 1, 3. And although there are many ways of multiplying matrices, there's like 3 or 4 different ways you can actually do the algorithm of multiplying matrices together. I will show you the one way that I think is the easiest. And then if you know another way of doing it, that's totally fine. But here's the way I think is easiest. You start with rows of your first matrix and columns of your second matrix. So if you take the first row dotted with the first column, because that's really what you're doing here, is you're thinking of the first row as a vector and the first column is a vector, and you're taking the dot product of those two vectors. So that first row, first column is going to be 2 times 4 plus 1 times 1. Also, something that I didn't learn until much later, but I think is worth knowing, if you take the first row of A and the first column of B, you get the entry that's in the first row and first column of your product. And that's always true, meaning when I take the first row of A dotted with the second column of B, I'm going to get the entry that's in the first row and second column of my product matrix. It's going to be 2 times 0 plus 1 times 3. Make sure you leave yourself enough space between these two things so you don't think they're going together. And then I've exhausted all the columns with the first row, so then I drop down to the next row. I say, okay, now I'm using the second row with the first column. That's going to end up in the second row and first column. And so it's going to be -3 times 4 plus 5 times 1. Now here's something audibly. If you could please turn it off, I would appreciate it. And then finally, second row, second column, -3 times 0 plus 5 times 3. And then we simplify. So we get, let's see, 8 plus 1, 0 plus 3, -12 plus 5, and 0 plus 15. Okay, probably the first. So after multiplying matrices together, it's really important to learn the second lesson. In fact, I want you all to do this next one. So I want you all to multiply B times A. So it's going to be the matrix 4, 0, 1, 3 times the matrix 2, 1, -3, 5. And again, it's rows of your first matrix with columns of your second matrix. So go ahead and multiply that out. So check it out. Just to kind of re-emphasize what I was saying before, in this first entry here, it's the first column of your first matrix dotted with the first row of your set. So whoa. Let me back that up. I said it completely wrong. It is the first row of your first matrix dotted with the first column of your second matrix. Over here, first row of your first matrix dotted with the second column of your second matrix. Second row, first column, second row, second column. You don't need to write out like dot products, but I really wanted to actually remind you that you're taking the dot product of these two things, where you're thinking of each row as a vector and each column as a vector. So what do we end up getting? We end up getting 4 times 2 plus 0 times negative 3 is 8. 4 times 1 plus 0 times 5 is 4. 1 times 2 plus 3 times negative 3 is 2 minus 9, which is negative 7. And 1 times 1 plus 3 times 5 is 16. And kind of the biggest thing to observe here that might be a kind of a new idea is that the order of multiplication really matters here. The matrix A times the matrix B does not equal the matrix B times the matrix A. So matrix multiplication is not a commutative operation. Interchanging the order of multiplication wildly skews the results, or might even make the other multiplication impossible. For example, if we look at, say, A times C, that's going to be the matrix A, which is 2, 1, negative 3, negative 3, 5, multiplied by the matrix C, which I've written down over here, 6, 1, 2, negative 1, 0, 1. And that's going to be totally fine. So it's going to be 2, 1 times 6, negative 1. I should say dotted with. So we're going to get 2 times 6 plus 1 times negative 1. So 2 times 6 plus 1 times negative 1. I'm writing this out for you. You should not write this out if you can do the math in your head. If you can be like, cool, 12 plus negative 1 is 11, you should write down 11. If you want to write it out, though, that's also fine. Just do as much as you need to do for these. And then 2, 1 with 1, 0 is 2 times 1 plus 1 times 0. And then 2, 1 with 2, 1 is 2 times 2 plus 1 times 1. Make sure you write it clearly enough so you can read what you've written after you've written it. And then now we're going to do the same thing, except now it's the second row with all the columns. So I get negative 3 times 6 plus 5 times negative 1. I get negative 3 times 1 plus 5 times 0. And I get negative 3 times 2 plus 5 times 1. And then simplifying everything, I get 12 minus 1. I get 2 plus 0. I get 4 plus 1. I get negative 18 minus 5 is negative 23. Negative 3 plus 0, and negative 6 plus 5. There's your product A times C. Whereas if you try to multiply the matrices the other order, C times A doesn't work. Because when you write it out, you get your 6, 1, 2, negative 1, 0, 1, multiplied by 2, 1, negative 3, 5. This row dotted with this first column doesn't work because they don't have the same number of things. This row is a vector with 3 entries. This column is a vector with 2 entries, and we cannot calculate their dot product. So this multiplication is not defined. There is a way to know whether or not the multiplication is going to be defined before you write anything out. And it's wholly dependent on if the inner dimensions of the matrices match. So I'll point out here, A is a 2 by 2 matrix, and C is a 2 by 2 matrix. And, oh, sorry, C is not a 2 by 2 matrix. C is a what? 2 by 3 matrix. And the inner dimensions, this second 2 along with this first 2, those guys match, which means the matrix multiplication is defined. And even better, the outer dimensions tell you the dimension of your resulting matrix. Why is that pen so terrible? So that 2 there, along with that 3 there, that tells you that your resulting product is a 2 by 3, which it obviously was. And then over here, the inner dimensions don't match, right? This is a 2 by 3, this is a 2 by 2, and that 3 and that 2 don't match. So the multiplication can't be done. Cool. What else? What else indeed? Sure. Oh yeah, we have a couple other things. So a transpose matrix, so written usually with a superscript of a T, although some people use a prime sometimes, but I don't think your instructor is. C transpose, read, is called C transpose. And you get it by interchanging the rows and columns. And we obtain it by interchanging the rows and columns of the matrix C. Or whatever your matrix is. So if C is equal to the 2 by 3 matrix, 6, 1, 2, negative 1, 0, 1, then C transpose is the 3 by 2 matrix, where what was the first row is now the first column, and what was the second row is now the second column. Or said a different way, what was the first column is now the first row, what was the second column is now the second row, and what was the third column is now the third row. So all of your rows and columns have interchanged. You can kind of think of just like it's kind of like you're taking the matrix and you're reflecting it across its diagonal like that. So this thing that was 2 by 3 became 3 by 2. In fact, like write numbers if you really wanted to, like you could, sure, this is going to look kind of silly. Let me grab another piece of paper here. But you could totally think of it as like, sure, this is going to be kind of fun, I think. 1 second. Let me show you what I really mean, because I think it's kind of cool. So I got my, yeah. So I took my 3 by 2 matrix, and then, so if you can't see it if I flip it that way. And it flips kind of down, like that's not really, no, so if you could see through it, you would see that this first column is 6, 1, 2, and the second column is negative 1, 0, 1. So it's kind of like you're doing a reflection across a diagonal line. Neat. What else to say about that? Why would we do that? Sure, that's fine. So I would say you should spend some time practicing matrix multiplication because it is a thing you will have to do. To that end, why don't you all try and calculate the following? Let's go ahead and find C multiplied by its own transpose, which is going to be 6, 1, 2, negative 1, 0, 1, multiplied by 6, negative 1, 1, 0, 2, 1. Multiply that out, showing as much or as little work as you care to. And if you finish early, then calculate C transpose times C. That's what I got. 41, negative 4, negative 4, 2. Let's look at the other one. Because there's something I want to point out here, and I'm rapidly running out of time here. So if we multiply these ones together, so I'm going to not show my work this time because it's a lot of work. So the first row, first column is going to be 6 times 6 plus negative 1 times negative 1, which is 36 plus 1, which is 37. And then, so when I do this, I kind of like draw little lines to kind of remind myself what I'm doing. So this and this, 6 times 1 plus negative 1 times 0. And then first row, third column, 6 times 2 plus negative 1 times 1 is 12 minus 1. Now I'm moving on to the second row, which means all my entries are going to be in the second row. 1, 0 with 6, -1 is going to be 6. 1, 0 dotted with 1, 0 is going to be 1. When I'm doing this one, I'm not even thinking of the second entry. I'm saying it's 1 times 1. I know 0 times whatever is not going to contribute. And then 1, 0 dotted with 2, 1 is 2 plus, doesn't matter. Or I should say 2 plus 0. It does matter. It matters at 0. And then finally, this row with these columns, 12 minus 1, 2 plus 0, and 4 plus 1. So the interesting thing here, if you multiply these matrices in the opposite order, you get matrices of different sizes. Also, these matrices both have a special property. They're both called symmetric. Because if you took the transpose of either of these matrices, it would look the same. So this matrix, let's call it D. D transpose here is equal to D. Right? If you flip that matrix across this diagonal, it's the same thing. Same deal here. If we call this product matrix E, it is true that E transpose is equal to E. And these are called symmetric matrix. Symmetric. Oh my gosh, can I say the word? D here is symmetric. So is E. A matrix is called symmetric if it's equal to its own transpose. So only matrices that are square, meaning they have the same number of rows and the same number of columns, can be symmetric. Because otherwise, if you took the transpose, you'd have a totally different size matrices. All right, what else do I have here? Oh yeah, very importantly, yes, cool, good. So again, I would point out it's good to practice multiplying matrices and good to practice knowing when you can or cannot actually multiply matrices together. But there's one very important matrix that we should talk about for sure. Well, it's actually one type of matrix to say. So these three matrices are called identity matrices. Well, there's a little bit more to it than that, but I'll leave it for now. So we have I2 is the matrix 1, 0, 0, 1. And I3 is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Or any identity matrix is a matrix that has ones on what we call the main diagonal and zeros everywhere else. So just to write one more of them out, I4 would be a 4 by 4 matrix, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. What makes this matrix special? Well, what's special about the number 1? I mean, a lot of things, but multiplicatively, 1 is the only number you can multiply something else by and get the same thing back. I should say, let me rephrase. 1 is the only number you can multiply anything else by and get the same thing back. 5 times 1 is 1. 7 times 1 is 1. Pi times 1 is pi. I said whoa. I was speaking too fast there. 5 times 1 is what? 5. 7 times 1 is what? Pi times 1 is pi. So anything you multiply 1, you get that same thing back. Well, this is the matrix version of that. Any matrix of the correct size, you multiply by one of these matrices, you get the same matrix back. For example, the matrix A, I'll make a new matrix, 3, 4, 1, -5. If you multiply this by the identity matrix, we're going to get the same matrix back. Check it out. 3 times 1 plus 4 times 0 is 3. 3 times 0 plus 4 times 1 is 4. 1 times 1 plus -5 times 0 is 1. And 1 times 0 plus -5 times 1 is -5. And it doesn't matter which side you multiply on as long as it's the right size. This is also going to be equal to 1, 0, 0, 1 times 3, 4, 1, -5. It's also true if your matrix isn't square. For example, we look back at our matrix C, which was, I forget what it was, 6, 1, 2, -1, 0, 6, 1, 2, -1, 0, 1 times, so to multiply by an identity matrix on the right, it has to be a 3 by 3 identity matrix. But if you did that multiplication, you would exactly get the same matrix back, 6, 1, 2, -1, 0, 1. You can check, right? 6 times 1 is 6, plus 0 plus 0. And then this with this is going to be 0 plus 1 plus 0. And then this with that is going to be 0 plus 0 plus 2. And then this with that's -1. That with that is 0. That with that is 1. Or if you multiply it on the other side, you'd have to have a 2 by 2 identity matrix times the 2 by 3 matrix C. So as long as you multiply a matrix by the appropriate identity matrix, meaning the identity matrix of the right size, you get back the matrix you started with. Okay. I should specifically say this is the multiplicative identity matrix because there is also, so just like with real numbers, there's a multiplicative identity. We call it 1 because when you multiply any number by 1, you get that number back. You don't get 1 back. There's also an additive identity. What number can you add to any number and get the same number back? 0. And there is a matrix additive identity, but it's way less exciting. It's just the matrix of all zeros. And we don't really use it for that much, but I felt like I should mention it. Yeah. So if you ever want to multiply a matrix by another matrix and get the same matrix back, this is the right idea. The identity matrix of appropriate size. And then, yeah, we can say one more thing here. So, sure, this is kind of, do we really want to do this? Yeah, we do. Okay. So let's do one more thing here. One more thing that is kind of interesting. So we can show that for any matrix, but we're going to limit ourselves to an easier example. So it's true for any matrix, but we're going to fix it in a second, that A times B transpose is equal to B transpose times A transpose. And although this is true for any matrices that you can multiply together, we want to make it doable. So we're going to say, show that for any 2 by 2 matrix, the AB transpose is equal to B transpose A transpose. And so really, this is just a process of multiplying a bunch of stuff out. So let's say that A is, when you're trying to say something like this is true, you can't just pick whatever matrix you want. You have to pick a general matrix without any entry. So we're going to say that A is the matrix A, B, C, D, and B is the matrix E, F, G, H. And then we're just going to calculate both sides of this equation. So A times B is equal to A times E plus B times G. And then A times F plus B times H. And then C times E plus D times G. And then C times F plus D times H. And then if we take the transpose of that, so AB transpose is just going to be equal to the transpose, meaning this row is now the first column. So my first column is AE plus BG and AF plus BH. And my second column is CE plus DG and CF plus DH. So that's this side of it. Now we're going to calculate the other side. So to calculate B transpose times A transpose, well, B transpose is EGFH, and A transpose is ACBD. Now we multiply this out. Let's see what we get. We get E times A plus G times B. We get E times C plus G times D. We get F times A plus H times B. And we get F times C plus H times D. And even though my multiplication is written in the other order, the multiplication of real numbers, order doesn't matter. So let's check. Is AE plus BG the same thing as EA plus GB? You bet. So is CE plus DG and EC plus GD and FA plus HB and AF plus BH and FC plus HD and CF plus C. Yep, they're the same. So interestingly, when you take the transpose of a product, it reverses the order of multiplication. And it's the product of the reverse order of transposes. It's kind of a neat thing. All right, that's all for today. We'll continue talking about matrices on Monday. We're quickly approaching finding eigenvalues and eigenvectors, which is really the thing you want to know for next quarter, is how to find the eigenvalues and eigenvectors of a 2 by 2 matrix. We don't really care about larger matrices in 17C. And wherever the attendance sheet is, if it could make its way up to me, that'd be great. And if you could hit the lights, that'd be great. Thank you. Yeah. Yes, good. Light. Thank you.
Thank you.
You're welcome.
Transposing vectors.
Sure. You mean the matrix? Like the last thing we just did? Right here? Or the other one? This one here? Welcome, of course. You too. Yeah.
Sorry, falling asleep.
I didn't even notice, so it's okay. Also, sleep is important, so if you need to sleep, it's all right.
Yes, sir. I'll be catching up tonight.
Okay,
Have a good one.
you too. You're welcome.
That's really good. Thank you.
You're welcome, yeah. On the Zoom.